Good afternoon. I welcome you all to this lecture session of the course Laws of Thermodynamics. Now, in this session, last session we solved two problems. This session also we will solve two interesting problems. Let us see the problem. This is the problem. We have discussed earlier regarding the entropy change. Now, this is a problem. A 12 kg steel container has 0.2 kg superheated water vapor, means superheated steam at 1000 kilopascals, both at 200 degrees Celsius, both the steel container and the superheated steam water vapor, the steam at 200 degrees Celsius. The total mass, that is both the steel and the steam, that is water vapor, is now cooled to ambient temperature of 30 degrees Celsius. How much heat transfer took place was taken out of the system, and what is the still water? Both these things makes a system still water entropy change. So, let us come to the board and understand the problem. The problem is like this. There is a steel container, this is the steel container, and there is steam. This is steel container, this is steel container, this is steel container, this is steam. Let the initial state is 1 is the initial state, and let 2 is the final state. Now, initial state, the temperature T is what is given in the problem. Temperature T is 200 degrees Celsius, that means 473 Kelvin. Now, the pressure of the steam, that is the initial pressure, because now the steel and the steam combinedly contains the system. So, steel has a temperature of 200 degree Celsius, that is 473 K, and steam is also 473 K, and P1 is given by 1000 kilopascals, that means 1000 kilopascals. Now, to find the property, we have to go through steam table, but first let us write the equation for first law. Okay, first law. What is first law? Now, if we consider Q is given to the system, actually it is taken out, but we will find it if we get a negative sign, then it will be taken out. In general, we do like this. Q12 is U1, U2 minus U1, that is the change in the internal energy of the system, plus W12. But in this case, W12 is 0. There is no heat transfer because it is a rigid steel container and steam. Heat is transferred out, but we have taken it in so that we can write the general equation. So, this can be written as Q12. Now, this MU2 minus U1 consists of both steel and the water vapor. So, for steel, it is M steel. Change in the internal energy of the steel is M steel, C steel into T2 minus T1. For a solid, the change in energy is the specific heat into mass into temperature change, plus the M steam into U2 minus U1 steam. So, now we know C steel is not given, but we know its value, I will tell you afterwards. M steel is known, mass of steel is M steel is 1.2 kg. M steam is given, what is that? 0.2 kg. 0.2 kg. So M still we know, T2 we know, T1 also, T1 we know, and T2 is also we know that T2 is, here I write, T2 is 30 degree Celsius, that means 303 K. So therefore, this part is known, this part M steam is known, but we neither know U1 nor know U2. How to find out? Now, from steam table you check that 1000 kilopascals and this temperature of 473 K, that is 200 degrees Celsius, is a superheated steam. How to check it? If you see this steam table 1000 kilopascals, you will see the saturation temperature is less than that. That means it is a superheated state. That means if I draw a diagram, TS diagram, you have come to know this in your earlier class, that this is a constant pressure line in TS diagram. This is the liquid line, this is the liquid line, saturated liquid state, all the points in this line, and this is the vapor line, that saturated vapor. Now this, if this is 1000 kilopascals pressure line, my state is like this. It is at a temperature, this is the saturation temperature corresponding to, this is the constant temperature corresponding to this pressure. So this temperature is higher than this temperature. This is the saturation temperature corresponding to this temperature, 1000 kilopascal. So this is at superheated state. So from superheated steam table, I find U2, U1, here I write. I find U1, I find S1, these are all specific values. This small u are the specific values. This will be required. And also I find the specific volume of the steam at initial state. This will be required. So these three things I find from the superheated steam table. Now I have to find out U2. Now how to find out U2? This is very interesting. Now only thing I know that this is at 303 K, final state is at 303 K. Now the point, I don't know anything else. Now whether this will be in a superheated region at this temperature, then its pressure will be lower, then this will be its existing pressure. This may be dry saturated vapor, this may be liquid, or this may be somewhere here intermediate wet vapor. That means a mixture of liquid and steam, wet vapor. How to do it? How to check it? One thing is that this process is a constant volume process, because volume remains constant. And since the mass remains constant, that means the specific volume remains constant. That is, the clue is that V2 is V1. That means I know V2. This V2 is same as V1. Now we check this V2 against Vg and Vf, that is the dry saturated liquid and dry saturated vapor in the saturated steam table. And you will see in this problem that VL less than V2 less than Vg. VL no, Vf is it. That means the specific volume of saturated liquid is less than V2. V2 is higher than that, but less than Vg. That means it is not superheated, it is not saturated liquid, but is in between. That means it has a dryness fraction x2 with some dryness fraction x2. Now when we have determined this, it is in this state. So dryness fraction x2 can be calculated by equating this. V2 is 1 minus x Vf plus x Vg. These two things we get from steam table, and V2 we know, so that V2 is V1, from which we have checked that it is in the saturated, that is vapor dome, that means saturated state but with a mixture of liquid and vapor. So, if we equate this, then we get the value of x2, sorry, x2. When we know x2, point is here, for u2 also we can find out 1 minus x2 into uf plus x2 into ug. And for S2 also, specific entropy 1 minus x2 into uf plus x2 into ug. So, this uf ug, sorry, SF, sorry, it is SF into Sg. So, these are from stream tables, that the saturated liquid and dry saturated vapor for specific volume, for internal energy and for entropy. That means I get V2 U2 S2 similar to this V2 V1 S1 U1 like this. So, these sets are known at both inlet and outlet. So, therefore, if I put this U2 U1 and M stream, we get the value of Q12, and this value equals to, if you put all these values, that is T2 T1 M steel, C steel, and if you consider the steel specific heat as point, this as 0.46, this as 0.46 they have taken, and this value equals to minus 1434.8 kilojoule. Minus, that means minus sign means the heat is coming out. Now, the entropy part is very simple. I can rub this thing. So, entropy change is entropy change of the steel plus the entropy change of the total entropy change, total system is delta S steel plus delta S steam, and this is equal to mass of steel is specific heat ln T2 by T1 plus mass of steam into specific heat into, oh no, mass of steam specific heat, I am sorry. So, this is delta S steam is m dot m steam into S2 minus S1. This is already obtained. S2 value we know, S1 value we know, S1 value we know, because from the superheated steam table I get this, from the saturated steam table I get this with this check, and then we can find out, and this becomes equal to, I tell you that equals to minus 3.699 kilojoule per K. Now, one interesting thing is there, that this problem has not told you to find out the entropy change of the universe. This is the entropy change of the system. This is minus, because obviously heat has been lost. This is minus sign, that means heat has come out. It is delta S of the system is like that. If you find out delta S surrounding, then you have to find out that this heat that is rejected, that is Q12, that is received by the surrounding divided by the surrounding temperature, that is 30 degrees Celsius, 303. The value of Q12 which I got earlier, 1434.8, this is with plus sign because surrounding is taken. So, this quantity minus this quantity is always positive, you do it, left as an exercise. So, Q2, Q12, if you put that value 1434.8, that is 1434.8 divided by 303, then you will get, this is more than this by magnitude. So, this minus this is positive, that means entropy change of the universe is positive. This is not asked of course in this problem. Okay. I hope you have understood this problem well. Okay. Now, I can rub this. Acha. Next problem is tremendously interesting. This problem you see very carefully. This gives you the concept of internal irreversibility, external irreversibility and entropy generated. Very conceptual problem. See that a computer chip dissipates 2 kilojoule of electric work over some time, and rejects that as heat transfer from its surface at a steady state temperature of 50 degrees Celsius to the ambient air at 25 degrees Celsius. Now, what we have to find out? We have to find out entropy change of the chip, entropy change of the universe, entropy generated within the chip, entropy generated outside the chip, total entropy generated. All these things, entropy change of the chip, entropy change of the universe, entropy generated within the chip, entropy generated outside the chip, and total entropy generated, which is obviously C plus D. This problem is very interesting problem. Now you come to the board work. The problem is like this. There is a chip which is at steady state temperature 50 degrees Celsius because of an electrical work transferred to it. That means electrical work. That means some voltage, some electric current passes through it, I, across a voltage. That means some electrical work, simply a resistor concept. You consider a chip which gets heated. Heated means this electrical work is converted into intermolecular energy. But at the same time, it gives heat Q to the surrounding, which is at what temperature? Surrounding at 25 degrees Celsius temperature, TA at 25 degrees Celsius. And in such a way that the temperature 50 degrees Celsius at the chip surface, consider it in the of the chip itself. Chip is a very thin material, that it is at 50 degrees Celsius at steady state, doesn't change. That means the heat which is transferred is given by the electrical work, steady state. That means by first law that Q is equal to, if you write the first law, Q is equal to delta U plus W. Chip is at steady state means delta U 0. That means Q. It is from common sense that to keep the temperature constant for the chip, the electrical work added must be equal to the heat transfer. That means electrical work change the intermolecular energy, but at the same time heat transferred out makes the intermolecular energy remains the same. So, chip is at the steady state and this steady state temperature is 50 degrees Celsius. This is very important point, the chip is at steady state. So, delta U 0, so Q is equal to W. That means the entire electrical work is finally transferred as heat to the surrounding. First dissipated in terms of intermolecular energy which raises its temperature, then dissipated to the surrounding, and they are equal, so that temperature remains same. Now we write this expression delta S Now, this is a highly irreversible process, because of this internal irreversibility in the chip, the temperature is increased. Well, by virtue of which it transfers it to the surrounding. So, there is this is highly an irreversible process. I told you the example. This is because of the chip resistance, that electrical work is being dissipated in terms of, or transferred in terms of, converted in terms of intermolecular energy, highly irreversible process. So, delta S I. But now, since the chip is at steady state, delta S is 0. Delta S is 0. For this chip, since it remains at steady state, its change of entropy is 0. So, first question is delta S chip equal to 0. Since equals to 0, delta Si is delta Q by T. Now, in this case we can write delta Q by T plus delta SI is 0. Or delta SI, that entropy change due to internal irreversibility, is equal to, this is first I am writing, this plus this delta Q by T is negative since it is going out, and since T is constant, it is Q by T chip. I am writing this here and this here. So delta SI is Q by T chip. That means Q, which is going out to the surrounding, divided by the chip temperature, gives you the delta SI. That means this is the entropy generated due to internal irreversibility within the chip. So another answer is there, one answer is there. So this is the entropy change due to internal irreversibility of the chip. But this is not the entropy change of the chip. Entropy change of the chip is this. So this is entropy generated. Sorry, not entropy change, I am sorry. Entropy generated. The word is not entropy change. Sorry, entropy generated within the chip because of that means within the chip entropy is generated because of the internal irreversibility. But the entropy change is 0. This is because delta SI and delta Q by T balance each other. Delta is 0 I have got, is a steady state. From other point of view, you can explain that entropy is generated due to internal irreversibility, and I told you in the last class, just last but one class, before the last class, that there may be a situation that heat loss and the internal irreversibility may balance each other, so that delta S is 0. So that this is balanced. So entropy generated is Q by T chip, which you can find out by this. Q is 2 kilojoule, 2000 joule divided by T chip. T chip is 273 plus 50, and this becomes equal to, you can find out the value. You can find out the value that entropy change, entropy generated in the chip is 6.19 joule per K. 6.19 joule per kgK. Joule per, sorry, not kg, joule per K. I am sorry, joule per K. Okay, now what is the entropy generated? Next one, outside the chip. Outside the chip entropy generated, that means this we call, this is because of the external irreversibility I told, because of the heat transfer due to a finite temperature difference 50 and 25. That means this will be Q by T chip, this is minus, plus the same Q by T surroundings, TA. Now Q is equal to 2000 joule, Q is equal to W is equal to 2 kilojoule, 2000 joule, and you put the value of T chip, that is 50 plus 273, and value of TA, what is TA? TA 25, 273 plus 25, and you get that value of entropy generated externally, that is entropy generated internally due to internal irreversibility, and this is entropy generated due to external irreversibility. Entropy generated due to external irreversibility. Due to external irreversibility. This is due to internal irreversibility due to external. So total entropy generated, total generated the entropy generated, delta S total, I am not writing total, generated total is entropy generated due to internal irreversibility and external irreversibility. So internal irreversibility entropy generated is Q by T chip, and external generated entropy, you can calculate that, but I am writing in this form, minus Q by T chip plus Q by T, and this cancels out. That means total entropy generated becomes Q by T. The entropy generated externally if you calculate, you get this value. You get this value, that 0.519 joule per K. Entropy generated externally 0.519, that means if you equate it, 0.519 joule per K. So you can add these two, but it is written first in this fashion to show that it simply becomes Q by TA, and if you calculate Q by TA, it will be this plus this, obviously, because this and this cancels out, so this plus this you can get, but by formula it is Q by TA here. Now if you see from other point of view, if I write delta S universe, that is delta S chip, without the concept of entropy generation internally and externally, just I find out the entropy change of the universe. I know the entropy change of the universe is entropy change of the system, which is the chip, plus entropy change of the surroundings. And entropy change of the chip is 0, surrounding will be Q by TA. Q is equal to 2000 joule. That means we see that entropy change of the universe or total entropy generated are the same. That means the classical statement in classical reversible thermodynamics in terms of entropy generated of the universe becomes equal to the delta S generated, total entropy generated, which equals to delta S I plus delta S E. That means you can look the problem from two angles. One is the irreversible thermodynamics angle, we can find out. That's why so many things have been asked to find out, that entropy change of the chip is 0. So entropy generated due to internal irreversibility is by this equation, which is very important equation. I told you in the earlier class that delta S is 0, then delta Si is minus del Q by T. Here in this case del Q by T is negative, so this is del Q by T, and this del Q by T becomes Q by T because this temperature is constant. Otherwise, we have to integrate if this temperature would have varied. So this is simply Q by T chip. This is the numerical value. Now entropy change due to external irreversibility. I told that external irreversibility is the irreversibility due to heat transfer through a finite temperature difference. So therefore, through a finite temperature difference, heat transfer through, so entropy change for this type of irreversibility, heat transfer through a finite temperature difference will be like this. The chip has this entropy decrease and this has this entropy increase. So therefore, delta AC is like this. This is the boundary temperature of the chip, where it transfers the heat to the immediate surrounding. So this is delta AC, entropy generated due to external irreversibility. So total entropy generation, both due to internal and external irreversibility, is then this cancels out delta Si plus delta S, delta Si plus delta Se. This is delta Se and this is delta Si, so that it becomes Q by TA. Now if you calculate delta S universe at delta S system plus delta S surrounding, that is chip plus surrounding, then this becomes equal to again Q by TA, because delta S chip is 0. That means delta S universe is equal to the delta S generated, delta Si plus delta Se. So therefore we see that all these aspects have been covered here, that entropy generated and the entropy change of the universe. So in the conclusion of this lecture, I like to tell, this ends your lecture on entropy as a whole of the second law of thermodynamics. I just summarize it in brief, that we started from the second law concept as a directional constraint or a unidirectional characteristics of a process, and we there saw that there are some processes occurring spontaneously in nature or man-made which are one directional, but many processes which are both way possible to occur, they make a permanent indentation. That we finally come at the end that that occurs in such a way that entropy is generated in the universe and entropy change of the universe is greater than 0. We learned Kelvin-Planck statement and the Clausius statement that a heat engine to develop work continuously from heat, it has to interact with two reservoirs. Heat has to be rejected. That means continuous conversion of heat into work is not possible in a cyclic process. But heat can be converted into work by not possible by the same amount. That means the same heat, the equal amount of heat cannot be converted into the same amount of work. The heat cannot be converted to work by the same amount in a continuous process by a cycle. Thermodynamic cycle is required for continuous conversion. But in any process, heat can be converted into work. That concept should be there. Now, after that, I tell you certain tidbit concepts of thermodynamics. Many people do not have that. Q is equal to delta U plus W in any process, single process. Now, there may be a process where delta U is 0. For example, if you take an ideal gas and if you supply heat and get work in a way that the temperature remains constant, then ideal gas internal energy is a function of temperature. So, therefore, internal energy remains constant. So, delta, there may be process where delta is 0, Q can be converted into W by the same amount, but it cannot be converted into W continuously in a cyclic process. That is the restriction by the second law, is Kelvin-Planck statement. Clausius statement is very simple, heat cannot be conveyed spontaneously from low temperature to high temperature. The most important theorem of second law is the Carnot's theorem, that a reversible engine operating between two temperature levels, source and sink, has the higher efficiency than an irreversible engine. And all reversible engines have the same efficiency, whereas all irreversible engines have different efficiency. Even the maximum of that is less than that of a reversible engine operating between the same two thermal reservoirs, from which we finally deduced the concept of absolute temperature, which is defined as the ratio of the absolute temperature of the two systems equal to the heat added and heat rejected by a heat engine from those two systems. From one, heat is added, to another one, heat is rejected. And then from that, we had the concept of entropy, which is defined in terms of its change, that entropy change in a process is given by the integral del Q by T if the process connecting the two states is connected by a reversible process. That means it is defined as the delta Q by T in a reversible process, integral of delta Q by T in a reversible process. And delta Q by T in a irreversible process is less than this delta Q by T in a reversible process. And therefore, it is less than del S, entropy change. Just now the problem we solved, that's why entropy change of a system is expressed at delta Q by T plus some positive quantity, which is entropy change due to internal irreversibility. Okay. This is the concept. Clausius, this is Clausius inequality. Cyclic integral of del Q by T is 0. If T is the temperature of the system, working system operating in the cycle, then this is endo-reversible cycle. That means internal irreversibility is 0. So, in that case, we can tell that del Q by cyclic integral del Q by T equals to 0, where T is the system, working system temperature. But if T is the temperature of the surroundings, source and sink, then the cycle has to be both internally and externally reversible. So, this is very good concept, very useful concepts you have to remember for second law of thermodynamics. We have solved some problem in second law of thermodynamics, and I think this is all. And for the second law up to this, but next class, this is all not for the second law, but in the next class we will be discussing, Professor Suman Chakraborty will take the entropy transport for an open system, so long which I have discussed related to entropy change and entropy generated in a closed system, but he will discuss the entropy transport in an open system, which is very important. The way we discussed the first law applied to a closed system and the first law, the conservation of energy principle, applied to an open system, and then he will discuss that. With that, our discussion of second law will end. Okay, thank you.